All right, so we're back, and in the episode on probabilities, and let's talk about. Let's continue. So far, we were just like dealing with a toy example. When we will have to model something in terms of probability distributions, we clearly observe that not all phenomena depend on each other. There are phenomena that, or in theory, everything depends on everything, but for not getting crazy, you tend to isolate things. You can tend to isolate causes, effects, and things that are completely, different from each other. They don't interfere with each other. An example could be if we have this word with Orazio, we take an elevator, and we put an elevator that Orazio cannot take, right? Because otherwise it would change the number of possible locations. So an elevator which is there, and then we could. That's another thing, another event, another generator of events, another variable in our world, another dimension in our world, which is the floor at which the elevator is. Right? In the end, in order to capture one configuration of this world, I will have to tell you where is Orazio, what signal strength is it measuring, and where is the elevator, because I put the elevator in the world. But the elevator has nothing to do with the robot if the robot can't take. So, how could we express it in the language of probability? We could simply say that the probability that the elevator A is in a certain location, given the position of Orazio, or given something else, is equal to the probability of the elevator itself. So basically you're saying that the conditioner, the knob, you can spin the knob as much as you like, the distribution doesn't change. Okay? That's the way. Now, if I have two probabilities, two events which are disjoint, which means that do not interfere with each other, can I construct a joint probability table? Yeah, for sure. No one prevents me from doing so. It's not the smartest thing in the universe, but I could do it, right? I could define the elevator, the event, Orazio and elevator, and I could tell what is the probability that the elevator is on the 3rd floor and Orazio is in the cell 76. Isn't it an event? Yes. So it can be true, yes. So I can do that. And then I might ask, hey, I'm interested in doing inference in this fantastic world, and I want you to construct me the joint probability table of the event, elevator, and the events, the domain, elevators and robot positions. So then you say, you know what? I know how to do it because I've given you the chain rule before. I've given you P of A given B times P of B, which is equal to P of A and B. But then, given that P of A given B is equal to P of A, right? Because the elevator A is independent from the Orazio location, so previous slide. If two events are independent, if A and B are independent, knowing B doesn't tell me anything about A. So P of A given B is equal to P of A. Right? Do you agree with that? And then before we had encountered the chain rule, which was here. Right? I could simply apply the chain rule and tell that if two events are independent, P of A and B is equal to P of A times P of B. And in terms of probability table, what I will have to do is simply to multiply the two distributions. So only the difference when you have this conditioning thing, can you visualize it for a second? What do you expect in this machinery over here if the signal strength would not depend on the location, right? How would you expect that this histogram here would be with respect to this histogram here? Identical. Because if I move along this line, this histogram doesn't change, right? So they would be identical. So basically, I can construct the joint probability table if I'm interested in. Oh, sorry. If I'm interested in that of two independent distributions just by the outer product, so to say, of the two corresponding vectors, if I am thinking in terms of matrices, right? However, we're not interested in that. But this gives us also a quite interesting independence test. Because if I give you a joint probability distribution whatsoever, represented as a table, and then I ask you, are these two variables independent? How would you do it? With the instruments that I've given you now. I give you a joint probability distribution, and I want you to tell me whether these two variables actually influence each other. Now, let's say, can we calculate P of A from the joint? Yes, we just collapse around one dimension, right? Can we calculate P of B? Yes, we collapse with respect to the other dimension, right? And then we have P of A, P of B. We can recalculate the probability table, and if it's the same as the input, then this means that the two objects are independent. If it's not the same as the input, then the two objects, the two sub-variables, the two variables are correlated. Okay? You say, I assume they are independent. I compute the marginal, I compute the other marginal, then I reconstruct everything. If I reconstruct everything and it's as if it was under the assumptions that they were independent, then this means that they were independent in the first place. All right. Now, and that's basically what I've said before. Independence test. Of course, you don't do it, but it's just a simple mental exercise to focus the concepts that we have been talking about so far. Right? To see how with little bricks one can start playing with. Now, let's do something cooler. Let's start localizing our robot. Now, we have the joint table over locations and strengths. We do have it, because we conducted the experiment before. We conducted the experiment on the signal strengths, we conducted the conditional to the locations, we conducted the experiment on the locations, and with those two, we were able to construct a probability table of signal strengths and locations. All right? Now, if I tell you, I measure the signal strength S2. This is a statement. You have the knowledge, because you conducted the statistical experiment. But my statement is, because I registered it very now from the sensor, and the statement is signal strength equal S2, right? If I say so, and I ask you, where is the robot? What's your gut feeling? Can you tell me something?
It could be places.
Yeah, it could be. Who knows? Maybe there is some place where you never observe the signal strength S2. But you have some information in the joint probability table. Now, let's reason on this joint table. Remember that each of those is an event, and it's an independent event, right? If I tell you, you measure the signal strength S2, what does it mean? It's a fact. It means that all other items of your probability table can be disregarded because you're not interested in them. They did not occur. Okay? So we have to focus our reasoning on this line over here, which is the line of the table where the measured signal strength was S2. You didn't measure S4, you didn't measure S3, not S1, you measured S2. All right? Very good. And that's gonna be it. So you say, okay, I'm fine, I'm there. No, this is the probability distribution. But I asked you not the probability of any event. I asked you the probability of all events. So like, if you look at this, you would see as if it was a histogram, which is a little bit higher in the correspondence of the places where the robot can be, and lower in the places where the robot cannot be. Observe that basically if in the joint distribution, if the robot from this cell never measured the signal strength S2, here I would have a 0. If the robot on this cell, it always measured, or from this cell it measured always the signal strength S2, which number would I have here? No. It's a joint distribution. It's 1 times the probability of being in location L1. And your colleague said 1. No, it would be 1 times the probability of being in location L1. And imagine that. Imagine that my joint table is made in a way that I only measure the signal strength S2 from this location. So if I am in location L1, I only measure signal strength S2. And if I am in location L100, I only measure signal strength S2, and there is no other location between here and here where I measure signal strength S2. So basically I will have 1 times probability of L1 plus 1 times probability of L100, right? So I will have 2 peaks in this line, which are in correspondence of the positions where the robot can be. Or just see it this way. We are taking this surface, this thing, and we are slicing it in the dimension that is consistent with the occurrence of our event, which is S2. All right? Just think it about volumetrically, you know. You have this surface that with a lot of bumps, then you cut along S2, you look at, you cut, you have this surface, 3-dimensional. You cut along S2, before you were seeing the 3-dimensionality, then you move on a side, and you see this mountain, right? Very good. But that's one problem, that this object, this slice, is not a probability distribution, because everything on the grid needed to sum up to 1, all right? This thing here is not a probability distribution. However, we could make it become a probability distribution. How? Ensuring that all the values sum up to 1. And how? By normalizing them, which means by multiplying them, each of them, by a factor that ensures that their sum is equal to 1. Okay? One second. So now, observe what can we do. We can take all these values over here, and this is the probability mass of the event I'm measuring the signal strength S2. Okay? We can sum all this value, and we get P of S2, right? Which is the event that we have measured. This is going to be the entire probability mass that I have on that row. Now, if I take each of these values over here, and I divide them by P of S2, in fact, I have conducted the normalization. Because I have ensured that everything sums up to 1. Doesn't it sound like the Bayes rule? Or something similar? Not really, but I mean, it's some sort of interesting thing. Tells me that I can get the conditional distribution over the location given a fact by taking the joint distribution and dividing only the line I'm interested in by the probability of the cause of the condition of the fact S2. Do you see that? I mean, if you want to visualize it, I have this 3D grid. The fact that something happens means that I just take a stripe of it, I ignore everything else, and I lift this probability mass, this mass, to be a probability mass, magnifying. Okay? Now it's kind of interesting because all the probability became a game, right? Marginalization, conditioning is slicing. Chain rule means taking a cause and multiplying it and obtain a joint distribution over the cause and the effects given the cause by taking each instance's possible probability value of a cause and projecting it into the effects space, which would be the signal strength in this case, for each possible thing. And what you get is that you move a conditioner into the other side, and you have a joint. Okay, guys? All right, now visually, how do we localize? Oh, we conducted an experiment. We were able to localize the robot, right? More or less. Only by measuring the signal strength, one signal strength, we were able to say something about it, or at least to exclude locations. All right. You had a question?
Yeah, I didn't understand. How can the sum of the row be greater than 1? Because you said
It's not greater than 1.
greater than 1.
Smaller than 1.
If we have to normalize.
Yeah, but the normalization doesn't. Normalization can also be done with a number which is smaller. So if I divide by a number which is smaller than 1, in fact, I'm magnifying.
Okay, so they don't sum to 1 because they are
Smaller. Your colleague says, hey, because we normally think about dividing by a number. When we think about division, we think a division by a number which is smaller than 1. But in this case, the denominator of this formula over here is always smaller or equal to 1, which in the end results in lifting the probability mass. Thanks for the question. All right, so like if you want to localize Orazio, it's quite easy also visually. You say, oh, this is my joint table, I'm happy with that. I just pick up the event that just occurred, and I evaluate how likely is the event itself, because if the event is very unlikely, well, I mean, this means that presumably this number will be very small, but doesn't matter because the event has been measured. If it has been measured, then I take this element over here and I divide it by the inverse of this. Take this and I divide it by the same number, thus conducting the normalization. Okay? So we encountered, repeat, the axioms, marginalization, chain rule, conditioning, which is what we have done right now, which allowed us to localize Orazio. Remember one thing, the marginalization is the action. When you see P of A and B and you want to get rid of one of the two, you say I marginalize out this variable, which means visually collapsing. Now, there's a third thing, which is passing through functions. Let's say I have x, which is a my funky random variable, which we got what it is. It's a variable of which I don't know the value. A variable with attached a probability distribution or a probability density. I have a function, a deterministic function. Let's call y equals f of x. Is it dramatic? You can think about it, even the function can also be discrete, right? Can also go from discrete to discrete. Doesn't really matter. Doesn't really matter. If x, can I calculate y, a random variable y, such that its probability distribution is obtained by taking the probability distribution attached to this capital X passing through f? The answer is clearly yes. How would you do? Well, let's think about it. Let's think about it for a second in the discrete case. Y, so f of x is a transformation, which means that takes one element of the domain and projects it onto the codomain. No? While it's doing this projection, the probability mass attached to the value x reasonably moves to the codomain, to y. So if to an x I will have a y correspond, x1, y1, x2, y2, x3, y3, right? Agreed? Very good. So I'm moving the probability mass. But I might also have the two values of the input space produce the same value in the output space. No? It's the case of a projection, for instance. No? When you, with a camera, you observe something, you have that all the points which are collinear with respect with the line of the observer, they all project on the same pixel. Right? Well, what is the probability of, how do I obtain the probability of this new, the distribution of this new random variable? Well, simply, I take an element of the codomain, so of the transformed element, I take this element, and in order to calculate its probability, I go back through the inversion, trivially, if I can invert f. But if I can't invert it, I will have a family of values in x that applied to f produce the same value y. Right? So this value y will receive all the probability mass from all the elements of the domain that project onto the codomain. Right? And then I have a probability distribution on y. Okay, guys? Is it reasonable? I guess it's intuitive. And that's what is what happens when you take a random variable and you apply and you calculate a function of a random variable. What you will get is another random variable which will have a different distribution, which can be obtained from the distribution, the input distribution by doing this operation. All right? Now, what we've seen, we talked about functions. Now, let me introduce another concept, which hopefully it will be the last of today, which is conditional independence. Now, we have a lot of money. We received a donation because of the fantastic lessons of probabilistic robotics, and we decide to invest this insane amount of money in buying an access point, right? We buy another access point, we put it somewhere, maybe in a room that was poorly covered, and let's also imagine that this access point works on a different frequency, spectra, whatever. It's completely different technology, no? Access points 2.0, whatever things that the marketing can say to sell you, well, a different thing, right? A different things. So that they don't interfere with each other. Otherwise, that would be interesting. And we take, let's call this access point B, and we conduct another experiment like the one before, right? Measuring the signal strengths. We put it in the environment. Fine. Now, what can we say? And of course, having put another object, our robot will have two antennas, one that will reveal the signal strength of the first, the other one which will reveal the signal strength of the second. We augmented our domain with the signal strength of the access point SB. Now, what can we say? We said that the two things are, no, they don't know anything each other, they don't interfere with each other, they're fine, right? And if I ask you, what about P of SA, signal the joint variable, joint distribution of SA and SB? What's your feeling? Let's reason on the physics of the phenomena, right? On what you expect, because that your intuition should be driven by what you expect to happen in the real world. We're not doing, anything exceptionally abstract. What do you think about this distribution? Are these two variables dependent or independent?
First thing, I think that if ADSA is greater than 0, the other one is 0, because you said that they don't...
Your colleague said if P of SA is greater than 0,
the other one is 0.
the other one is 0. This is the probability of the signal strength. So can I have two antennas, right? If I am in a middle location, I could, so your colleague said, I'm thinking that, but that's close. I'm thinking that if P of SA is greater than 0, then the other one should be 0. This is what your colleague said. But two different antennas.
Okay, so they can, if you're the middle, you get the maximum signal.
You get half, I don't know what a maximum, but you get something from one and something from the other. Reasonably, we expect that the signal strength will decrease with the distance, right? Reasonable. Imagine, right? So in theory, we could also guess that in an ideal world, measuring a signal strength will impose that the robot position should be somewhere on a donut, on a circle around the access points at that distance, right? Anyway, you caught something. The two variables, in fact, are not independent, because if I measure if I am very close to S1, and if I measure, assuming that they are in different locations, right? If I'm very close to S1, automatically I can't be close to S2. So I'm expecting to measure a very strong signal strength from one and lower from the other one. But if I measure a strong S1, I can expect that S2 will be weak, or will be not as strong, right? And vice versa. So the two variables are not independent. However, there is another story. So they are not independent, and that's pain, because it means that we can't do much of an inference. But if I tell you that you know the location, so the location is given, right? If the location is given, the location renders the two signal strengths independent. Because the two signal strengths in the phenomena, so the signal strength is a byproduct of the location of the loop, right? So if I would know the location, right, given L, I put the location there, then in this way, the location, the knowledge of the location allows me to select basically the two different instances of experiments that I have done before in the table, one on the signal strength as SA and the other one on the signal strength as B. And given that the location is the only way, the only latent variable that can influence these two phenomena, because in this ideal world, everything, what changes is the robot position that changes everything, right? Is the missing link. But if I give you the robot location, then the first access point doesn't care about the second access point. I mean, you know where you are. And knowing where you are is the only thing that enters in the model of the access point. The distance between the antenna, your antenna and the antenna of the access point. Right? But if you don't know it, then it's different. So then we can introduce the concept of conditional independence that we can write in this way. We say that two events, SA and SP, are conditionally independent given L, if we can write the following. If you remove the L from both formulas, try to remove mentally the L, and then I'll show you this. This is exactly the same as the other one, only that we removed the L, so to say. And conditional independence comes from the structure of the problem, which is actually really what we will be doing in the course. The tools will be some and will be always the same, but the interesting bit is to look at the problems and to model them in a way that you can then have something small that you can treat and which is minimal. And normally this knowledge comes simply by observing the things and reasoning a little bit about them. Right? But how do I do it? Now everything is foggy. We will make concrete examples and then you will find it obvious. Now, oh, wow, I've been super fast today. I was supposed to give 4 hours and I managed with 1 hour and a half. Now, conditional independence. what we can say about all this machinery is one thing, that so far we were working with probability identities. So in these tables that we were constructing, we didn't put any particular number, right? What we got typically were identities which were only correlating tables, so to say, or functions. We didn't impose any special structure on the probability distribution. If there was a 1 or a 0 or something, everything was the same for us, right? And this is a very important concept to think about when you reason with these things. You are modeling phenomena. The function might morph, might change the shape of a probability distribution. But if you work with probability identities, the only thing that they can change your deductions is assuming or not independence in one point or in another, because typically independence allows you to simplify the calculations, because you can remove stuff in general. Now, another thing that I want to tell you is that all manipulation, all for deductions, all proofs that you will ever do with probabilities, starting from the axioms, and also starting from this stuff over here, which is a consequence, these formulas, marginalization, conditioning, function, and so on, which in the end is a consequence of the axioms, holds regardless the shape of the input distribution, first. And the second thing, which is very important, and we will use it a lot, is that you can, once you have an identity in the form that you see on the left, right? Here we have P of A and B, which is, here we have the chain rule, here we have the conditioning, and here we have marginalization, right? But in general, it can be also more complicated, because maybe this P of B is the result of a marginalization, which is a result of something else, so might be a big object, okay? Now, this is an identity. And I can tell you that if you have a probability identity in this form or more complicated, on the right of the conditioning bar, right, you can put a conditioning bar here, and you can add whatever you want as you add it in every single element of the probability table. Why that? For instance, here we have P of A, and here we have the chain rule, and here on the left we have the chain rule to which we added the same C in the after the conditioning bar of all the things. All right, guys? Is that clear? It's visible in the end. So why that? Now, can you think about the experiment that we have done with Orazio, with the signal strengths? At the beginning, the conditioning was the location, right? Which could be seen as an experiment. As long, now this means that you can add a particular, this could become the instance of the experiment that you're doing. But if the identities, if the structure was respecting the probability axioms, then they have to be true regardless the instance of experiment that you choose for conducting your thing. Okay? An instance means cell or something, the particular stuff, as long as it's the same everywhere. You can't pick one experiment here, the other experiment there, the other experiment. No, it has to be the same. The conditioning has to appear consistently everywhere. Okay? This is the rationale behind that. So this gives us some syntactic tools to manipulate probability identities. Now, if you are fit, I can blast you with another pack of slides in 10 minutes. Let's see what the folks at home answer, and then, and also what the folks in the lecture. Okay? The risk is that I will, guys, well, that's also the people. Most of them, they will be delayed, I guess. No, finished. That was the last slide of the pack. Guys, write your comments. Shall I continue? And maybe finish earlier the course? Are you fit? Do you feel you digest these things? Because a lot of things, they need a little bit time to be digested. I don't know, were you familiar with this stuff? I guess, yes? Did you sense it, or did this lesson provide you any different insight about the things, or?
In any case, it's a refresher that is useful.
Okay. Okay. Boom.
Sorry,
Here I am.
can you put these lines on the web so I can download?
Didn't I put them?
No, on the next one.
Ah, the next one. Yeah. Give me a minute. So they asked me to publish the slides. Wait a second. Here. I teach so many courses that I don't remember anymore the sites. I don't remember. Where are the repositories? No, com'era?
Ci sono due git clone.
Ah. No? Com'era? Git. Oh. GitLab. Login. So, copy. Okay. Just updated. I didn't link them on the web page, but come on, forgive me for that. Now for the folks at home, give me another. I need another 3 minutes or 5 minutes, and then we continue again because it's the Now I'm entering, soon I will be entering the fourth hour of teaching, so I'm getting used. Ho mutare il microfono, vediamo se faccio danni. Ok. Ragazzi, voi avete già fatto le reti bayesiani, Bayes-net? Una volta ero solo io che facevo queste cose, mo. Vabbè, non ti preoccupa, queste durano poco.
Probabilities, relative e augment. Ma proprio in generale della laurea? Sì, 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 vai, certo, vabbè, però c'è solo... No, io sono disposto il secondo. Allora, grazie a lei. Io sono inizio.
Ma poi venite da Mara, siete tutti di Mara?
Sì.
Perché ci sono quelli dei controlli che queste cose non hanno viste. Metà classe è controllo.
Ah, sì?
Sì.
Ah, sì, allora. Io ho dato un caffè, ragazzi. Vabbè, ma veramente avevo visto che stare da questo. Hai venato? Tu vieni, ecco, allora faccio un computer. Sì, andiamo a fare. Perché dici che è un'intelligenza artificiale che ti realizza tutto quello che vedi, per cui quando ti vai difficilmente ci vedi nada. Però consuma tantissimo, quindi non stancare il cervello. Ti registra no, perché ti registra tutto quello che vedi. E se sei giovane difficilmente ci vedi nada. Però è una fatica. Scusa, ci conosci un po'? Però in generale, no, perché stai scrivendo 50-60 anni, non vuol dire che possono diventare poi la gioventù su 5, su 3. No, è strano.
mia, sto completamente... Facciamo un'altra ora e poi se fermiamo ai 3. Ma voi come... Aspetta, quando è che ci avete il clash con AMR?
Io non lo so questo perché io sono un dottorando di aerospaziale.
Ah, ok.
Sto seguendo il suo corso OSHA.
Ah, ok. Quindi mo devo mandare all'altro. No, perché sennò, visto che mi sbrigo un po', perché queste una volta erano 45 minuti, e poi l'hanno chiuse, espanse, 60, cioè, vero bordello, e allora è difficile, non puoi, sono degli argomenti che ormai l'hai stabilizzati in quel tempo, non li puoi sbrodolare, altri che non li puoi accorciare, quindi rimane un po' bieca sta cosa.
Poi... La prima lezione ho seguito online perché dico, siccome cioè, mi è impossibile prenotarmi in aula.
Aspetta, devo vedere se ho il microfono aperto così posso dire... Ah sì. Aspetta, mi muto. Oh, guys, one question, which is here. The question is, can you write down the timetable on the chat thingy, the timetable of autonomous and mobile robotics, so that I know when I can use the slots. Or actually, on Thursday, do you have a clash in the entire 4 hours, or only only in 2 of them? Non mi scrivono? Ah, mo siete arrivati. Regà, Fox, do you have a clash in probabilistic a clash with AMR? Is it on Thursday? Today?
No, Tuesday.
Tuesday. Today it's fine, the time. The time today is fine. Okay. It's on Tuesday that you don't manage, right?
Maybe someone has an overlapping with planning and reasoning. But it was from the beginning, so I think there's no problem today. The problem is when AMR, which is mandatory, is overlapping with on Tuesday with your quiz.
Tuesday is the problem, not today.
Not today, Tuesday. Martedì.
Okay. Because, I mean, I could also do a killer, I mean, but...
6 hours.
No, because that would be 8 for me. Not 6 hours, but I could do, I could delete the lesson on Tuesday. And this means that we will run a little bit more here.
I don't know if you think that you can cover all the program.
I mean, I'm fast. The point is that you need times for seasoning, and it requires some exercises. So, like, probably, I don't know. Now, let's see. I'm just self-brainstorming. Let's see what the Fox have written. Jesus, I mean, yeah. I understand. All right. So, and then we have only 7, 4 in the lecture hall, which would make 11, plus all those that are following other things, I guess. Because this means all those that follow offline. I will check the number of playbacks later and see. All right. Normally we are around 30 students per year. So now if I see 11, 14, means that you can't monitor how many they are. I have to look in the forms. All right. Shift F5. And then they have answered in the thing. All right. So now, next episode, we laid down some recap of probabilities, and then let's talk about Bayesian networks, tool that some of you has encountered, some others didn't. Let's talk about them. Che ho fatto, fermi, ESC, Alt Tab, OBS. Okay. No, still streaming. Still streaming, yes. It's very dangerous. With only one monitor, it's a hell. No, niente. Alt Tab. Poi vai su OBS, ok. Clicca qua. So, let's go back to the scenario of before. And let's talk about the word that's laid down. We have 2 access points, we have an Horatio moving, we have 1 elevator. So what are the quantities that characterize one situation of the word in this scenario? Well, the signal strength of 2 access points, which floor the elevator is in, and the location of Horatio. So far, so good. Now, if we have 2 access points with 4 possible signal strengths per access point, we have 6 floors because it's not a very tall building, and we have 100 locations. If we want to calculate the joint probability table over all these events, of course in this case it's not really a table, it's maybe a tensor or something, it's a multi-dimensional structure because each dimension covers a value, right? How many possible disjoint outcomes could I have? How many possible situations in the word could I have? Many, right? Let's see how many. We have 4 possible signal strength for the first access point, 4 possible signal strength for the second access point, we have 6 possible floors, and we have 100 possible locations. So we are at 9,600 possible outcomes of disjoint events, right? Now, then we take an expensive cheap camera, a poor VGA camera, let's say, which has 10 by 10 pixels, and for each pixel produces 1 level of gray. There are 10 levels of gray. So, one image of the camera, one possible image, is one point in a space which is 10 by 10 to the power of 16. Because basically one possible image is one assignment of a value between 0 and 15, or between 1 and 16, as you want, to each possible pixel. Right? Okay? So we have 10 by 10 to the power of 16. 16, a lot, right? And then immediately this number here bumps to something which is not tractable, basically, because we have 9,600 times this 10 to the power of 32, which is a lot. Okay? Now, if we want to calculate a joint probability table, enough to challenge some good computer. Now, let's do a query. Let's do a query in this domain, because we have seen that we can still construct a joint probability table, right? The joint probability table contains everything, because it contains all possible dimensions of my universe. And then by actions of marginalization, conditioning, or simply just by counting all the events that match a certain fact, then I can come out with a number, which is the probability that that event is true. Or that in case I'm interested in all possible outcomes, I could compute another probability distribution through the operations that we have defined before. Right. Now, how do we compute P of SA, so the probability distribution over the signal strength of the first access point, given that the second access point measured the signal strength too? Well, the rule says that just by having this joint probability table, which contains signal strength 1, signal strength, we could take the line of the probability distribution that contains the line. Should be a hyperplane of the conditional distribution where the value of the signal strength is only S2. This is equivalent to what we were doing in the conditioning before, only that we have much more dimensions. And then we consider all possible intensity values, all other variables, right? We have this joint. Then we could delete all the variables that are not appearing in the query through marginalization. So this performs a selection into this joint probability table, because here I put a 2. Then I end up with something which is not really a probability distribution, is a probability distribution scaled down. But then still I could do the operation of eliminating all the variables which are not relevant, and we know how to eliminate the variable. We just collapse along the plane. So we could delete all of this. And then we end up in this probability distribution, and we use the bias rule, which basically means you marginalize, you normalize by the probability of S of B2. Okay? And this would be a way to resolve this query with this huge, gigantic probability table. The problem is that this is not tractable, and you try to avoid passing through the joint table as impossible. However, we could use the notion that we have seen before of conditional independence to model the problem in a more compact way. So we could observe the world, hence it comes the modeling part, and we notice certain things. The first thing is that the signal strength of an access point depends only on the location. This is what we already have seen before. The second thing is that the pixels on the image itself, the image that will be rendered, depends on where the robot is located. And not only, the pixels on the image are independent from each other, because you could imagine that the pixel is just a ray that comes out from the camera, right? If I know the location of the robot, I automatically know the direction of the ray. And if I know the location of the camera, in order to predict the value that I will measure on this pixel, I don't need to know the value of the other pixel. Right? So, also the pixels are independent. So, and the elevator lives in his own world. Of course, the pixel and the image are independent if all I need to predict an image is the location of the robot. If this is not sufficient, of course in a model of the world, but this is a constant. If this is not sufficient, the pixel might not be independent, because a pixel might carry on information of another one. If I have a person passing, if I see something like there, I might expect that the next pixel will be affected. So we can make order with a graphical model, which are the Bayesian networks. Many of you have seen Bayesian network. How many have never seen them? Please write it in the chat, and in 3 minutes I will look at it. But anyway, it's a graphical model. It's a way of painting the reality. It's a directed acyclic graph, which is the generation of a tree. So it's like basically it's a graph which doesn't have loops. Doesn't have loop, a directed graph that doesn't have loops, which means that the diamond configuration is allowed, so something like that, but you can't have something that comes back. Okay? There's only one direction. You go from the root or the roots to the leaves, but you can't go back. Okay? Where you have one ball per variable, one arrow between variables if the source influences the sink or the destination. Right? So, if we want to model this reality with a Bayesian network and show the independence, we could say that the location L controls the access point, or conditions the access point. The location L, the access point A. The location L conditions the access point B. Equally, the intensity of each pixel. The elevator AE is there alone, like an idiot, doing nothing. Okay? We just like have drawn the thing just to highlight the independence of the variables. Now, this is the legend of the thing, so with the pixel intensities which are I11, I1010, so we have 100 pixel intensities, and so on and so forth. Important thing, in a Bayesian network, you cannot have loops. Right? Now, in order to, are you convinced that with this sort of table, I might have much less numbers to store to represent this reality? Let's see. Are you first convinced that I have highlighted, like by imposing independence, I didn't lose any information from the phenomena by imposing this sort of independence? Seems reasonable, right? Because you use your brain. That's it. You look at the phenomena. So if this contains everything, then I could just store into this system attached to each variable, not a joint distribution or something, but just the conditional distribution. Which conditional distribution? The conditional distribution that goes from the source to the destination. For instance, in this case, SA, this arrow over here, SA, will contain the conditional distribution of the signal strength with respect to the location. This one here, this arrow here, will contain the conditional distribution of the location with respect to signal strength SB. Here I will have another table that will contain the conditional distribution of the intensities of the first pixel, so 16 numbers, with respect to the location of the robot, second pixel, third pixel, fourth pixel, and so on. Okay? How could I get this information? Just by conducting experiments, as before. Okay? And then I have the elevator, which is there alone. Of course, the root variable has no conditioning arrows, nothing entering. And then this means that it's not a conditional distribution, it's just an absolute distribution. It's just probability of location, probability of elevation. Okay, guys? Now, how many numbers do I need? I need 100 numbers per robo location. So here, 100 numbers. I need 4 times 100 numbers for the signal strength A, because I have 100 location by 4 possible signal strengths, and that's the conditional probability. I have 100 different histograms over signal strengths, 1 per each location. The same holds for SB. And then, how many numbers will I have in this table for this pixel? Well, the pixel has 16 intensities, so I have 16 possible values of intensity. For each of these 16 this histogram, I have one of these histograms for each of the locations. So I have 16 times 100, right? And then, how many of those I have? I have one of those per each pixel. Anyway, I have many less numbers to store, right? Which is good, because the less numbers, the more efficient the calculation. All right. Then, once we did this effort, and we managed to compress the knowledge that we require to represent a reality in less numbers, we can do some sort of inference. And so in general, we can say that this formalist introduces the Bayesian networks, where each node represents a variable, x, and it also stores the conditional probability of the variable given all the conditioning elements. If you have 10 variables over here that are influencing 10 different knobs that influence this phenomena, clearly you will have a much different, you'll have the same number in the conditioning part. These are the knobs that appear in the conditioning part. Now, let's do with this machinery an example of inference. Sorry. And what I'm asking is, I'm interested in the probability distribution SA of the first signal strength, given that I'm measuring with this pixel over here intensity 7. Okay? The two are independent. No, the two quantities are not independent by themselves, because the image is correlated to the location, and the location is correlated to the signal of the access point. They are not independent, the location and the pixel intensity and the signal strength per se, but they are independent if I would see L, the location. But I don't see it. Anyway, what could I do? I do the computing work. Terrible. Do the computing work, and what I could do straightforwardly is to compute the joint distribution, because if I have all the information to calculate the joint distribution. What I could. This is not what you do. But what you could do is from all these conditional distribution, you could recover the joint distribution, as before. Once you have recovered, just by doing the product of all of them. Once you have recovered the joint distribution, you do exactly as we were doing before. You marginalize out the variables that you don't need. So basically you do a lot of summations over all possible variables of this joint distribution over the variables that you don't need. And then at the very end, you can use the conditioning in order to determine, so this formula here, in order to determine the answer you need, which basically will perform nothing else than a marginalization. Here you see that I use this distribution here, these values here, I calculate the sum over SA, so I'm in fact deleting SA from here, which means obtaining P of I711, dividing this object here by P I711 gives me P of SA given I711. And that's the way. It's crazy, you don't do that. I mean, also, why do I have to bother about the elevator if the elevator lives in its own world? I could just like get rid of it. And that's obvious. Some considerations are just reasoning on the phenomena. Would we get the same answer if the elevator was not in the domain? Yes. It's independent, it's there. Up, down, it does its elevator life. Okay. Second question, do you think that if I would measure the intensities of 2 pixels and not only 1 pixel, would this give you more information? Sure? Yeah, but 2 pixels are more restrictive than 1 pixel.
2 pixels together.
If I would measure 2 pixels, not only 1 pixel.
I told
yeah.
the other one.
Okay. Yes. So the second answer is yes. If I would know 2 pixels, instead of only measuring 1, I could be more restrictive because maybe there are many locations where pixel 1 is intensity 7, but there are very few locations where pixel 2 is intensity 3. And if there are very few locations where pixel 2 is intensity 3, this means that I have a more accurate localization because I have 2 things that I'm measuring instead of 1, right? So, answer to the second question is yes. And then question number 3 is that, do you think that if we would know also not only the intensity, but if we would know the location, remember that we are interested in knowing the probability of the signal strength, right? If we would know the location, would we be in a better situation? So I said, the elevator, does it give you more information? Answer was no. 2 pixels, do they give you more information on the signal strength? Yes. 3. 2 pixels and the location, do they give you more information about the signal strength or not? What's your feeling? No, of course. We could also say more. We could say that given that the only way that the signal strength, the intensity can influence the signal strength is through the location, the fact that I know the location, and I know I measure it, it absorbs all potential information that can come from the camera, because the camera is irrelevant whenever I know the location perfectly. All right? Anyway, and that's the game of the Bayes network. So, there are some simple rules that can be used. The first one is the local semantics that says that each node, for instance this one, is conditionally independent, so is from its descendants, so its non-descendants, so like for instance this guy over here, given its parents. So if I give you all the parents of this, anything that you could just like cut the network here off, because you just like block, no, you fix it. Got it? It's also visually true, because you're blocking the causes, and then anything that this guy here can tell you is just like absorbed by these things. Any inference that you can do, this is the location, right? If I block the location, here I have the intensity of the pixel, and here I have the signal strength. If I tell you the location, nothing you can do here, like because the location absorbs, blocks all information that is coming up. Okay? So you could simply like cut off and forget about all the part of the network. And the second thing is the so-called global semantics. It's like how to manipulate. The game in doing inference in Bayesian network is to try to trim it, to remove the things that are not interesting in this reality, and then focus your effort, which is marginalization, like doing the join, only in the part that you really need to. Okay? The second thing is that each node is independent from the rest, given from the rest, not from its non-descendants, from everything else, given its parents. So this is the node. Every node is independent, which means that you can ignore all the remaining part of the network if you do the so-called Markov blanket, which is like, I tell you the parents of a node, obviously, the children of a node, block it. So if you put knowledge here, the fact given means you know them, you measure them. Or you evaluate the probability distribution. The parents are obvious. The children are obvious because if I know something about this, then this node over here is an effect of this node over here, right? So if I know something about that, then I could come back to the cause of it. We have done it before with the location, right? And then it's quite easy, this to understand, but what it's normally hard to figure out is the parents of its children. This is the stuff that people say, hey, how comes that I also need this guy over here, right? To know this guy over here in order to make this object here independent. This is something, why, right? I mean, the reason, just think about the following phenomena. Restrict to a network which is consisting of just these 3 nodes, right? Because this one here we have already blocked. So 1, 2, and 3. Okay? This phenomena here, let me think about an example. One thing that has to, okay. This object over here means, this variable over here means I have no money, okay? An event. Having money, yes, no, or few money. This event here means, I don't know, I bought new phone, and this event here means I bought a new book or whatever, a new something expensive, a new monitor, okay? So, clearly, if buying a monitor and buying a phone influences my not having money, right? Now, if this was here, was buying a monitor. If I know that I have no money, I might have no money both because either I bought a phone or if I bought a monitor, right? Now, having no money alone doesn't give me a lot of information about having bought a phone, which is this case over here. Understood? But if I tell you, I have no money, I bought a phone, do I have money? Did I buy a monitor? Then you can tell me no, no, you didn't buy a monitor because you bought a phone and you have no money, so like it's less likely. Okay, so you have that. An effect might depend on multiple causes, and in order to propagate back the information from the effect to one of the causes, you need to know all other causes that might have produced that effect. Okay? And this explains the parents of its children. So this is called the Markov blanket, copertina di Markov, when he was feeling cold. Okay. Yeah?
Why are we looking the parents of the children? Just
the parents
of the parents of
the parents, the children, and because the parents of its children are the causes, are the con-causes of its effect. And this is exactly what I was explaining now.
The grandparents of the children.
The grandparents we never said.
Why we are interested in it?
Why your colleague says, why aren't we interested in the grandparents of the children? Because they are blocked by this guy.
Okay, so it contains all the
information. Exactly. All right. And then let's use these rules to do some inference here by trying to avoid calculating the joint probability table. We still want to answer the previous query, which is, what was it? The signal strength given the intensity. So this signal strength given this intensity, right? We don't want to expand too many things, and then we start reasoning, okay? Now, first thing that we can say is that given that we don't know anything, we don't know this, we don't know this, we don't know this, we don't know any of them. If we would know, we could bring back some information, but in this way we don't. So we can just blast them away. We just ignore. The elevator has been blasted in the origin, so we don't care. And the second thing that we can do is that now we have a very simplistic bias net. We have one thing here, one thing here, one thing here. Then the first thing I would do is like, you know what? I go back. I take some information from I11 and I propagate back to L. How? Well, you could easily compute P of L given I11. Right? Massacra del rumore oggi. How? Well, how can we do it? Remember, here we have a joint table, a conditional probability table over all possible pixel intensities. Conditional probability table over all possible pixel intensity of the pixel 1, for each of the locations, right? So what we could do is to, this is a conditional, right? In order to calculate P of L given I711, what I need to do is to first calculate the joint distribution between L and I11. Therefore, I will have probability of locations and intensities of the pixel 11. We have the joint. We do it with the chain rule between P I11 given L and P of L, and we get P of L and I. And then we can do condition. Just went back. Conditioning means, okay, now I have the joint, I give you the particular value I7, and then you can do the calculation. And we have P of L, right, guys? We go back. And then once we have P of L, we change the shape of P of L. Before it was P of L given nothing. Now it became a new histogram, which is P of L given I17. We changed the shape. The domain of the distributions remained the same, only that we brought back and we modulated the information in order to change the shape. And then at this point, well, at this point it's obvious because we could straightforwardly use the chain rule to propagate information from this probability distribution, which is L given I711, we go down. So when we bring back the information, we bring up the information, we change the probability distribution of the variables when we are incorporating things, because we're kind of deleting the stuff on the bottom. We change the shape and then we propagate down the value. When we go down is easy because it's just chain rule in order to do that. Now, this was, I have to tell you guys that I was forced to insert this lecture on bias networks because in the past they were not treated. Now it's just a glue, and I think that for the students of control engineering, if they didn't see this formally, is an introduction. But this is the only time that we will be seeing that before filtering. So next time we will see dynamic Bayesian networks, and we will dive through filtering. I think that there is enough meat on the pie for the first two lessons, because otherwise it will become too much. Next lesson needs to be done in a continuous manner, and now I will be wrenched. So I would even say that we can stop the lessons now, and now I go back to the video thing. And if you want, Barbara, if you open a Zoom thingy and you broadcast it with the email, I will be able to talk to all the students at the end of the lesson. Please, Barbara, do that. Thank you. So, see you on Zoom, and meanwhile I answer questions.